Hello everyone. Today I will talk about using interactive tree improvers to formally prove properties about generalized potential heuristics for PDL domains. This work is in collaboration between me and Florian Pommerening and Augusto Corrêa. And I'm Mohammad Abdulaziz. So I would like to just make sure that I tell you that this work is preliminary. So I will just try to introduce the general problem to you and give you a light overview of our technical contributions, and then give you an idea of where I think our approach can go in the future. So the general problem which we address is the following. Given a lifted planning problem, that is to say a PDL domain which represents an infinite number of grounded problems, how do we prove a certain property holds for all of its instances? An issue there is that proving such theorems for PDL domains can be in general be impossible due to theoretical limitations like undecidability or semi-decidability, and our proposal is to use an interactive theorem prover to prove such theorems for every domain. So you're given a domain and then you use an interactive theorem prover to prove that. In the rest of this talk I will introduce another interesting property which we want to prove for domains, and which is namely that a certain heuristic is descending for this given domain, and then I'll skim our technical contributions towards making such proofs possible using an interactive theorem prover. So in a nutshell, we want to prove that given a planning domain description in PDL and a specification of a function mapping states to natural numbers, where those states can be of any instance of that domain, we want to prove that using this function as an A-star heuristic will lead to solving any instance of that planning domain quickly. That's more precisely in linear time in the value of the heuristic. The heuristics we consider, we denote them here with this big H or this capital H, and then it maps, as you can see, the set of all possible states of instances of the given domain sigma to natural numbers. And I want to show for such a heuristics that for any instance pi of the domain sigma and for any alive state S valid with respect to the planning instance, there is an alive successor state S prime such that the value of the heuristic at S prime is smaller than the value of the heuristic at S. We refer to a function satisfying this condition as a descending heuristic. If we can prove that a heuristic is descending, that implies that this heuristic can solve any instance of the given domain in linear time using A-star search. Our approach is to use interactive improvers to perform this proof. The interactive improvers are mechanized formal mathematical systems in which one specifies definitions, statements, and proofs in a formal language, and the interactive improver makes sure that the proof only follows from a specific set of axioms. In our case, we use the interactive improver Isabelle Hall. An example proof of using that system is on the slide here, where proof of the fact that the square root of 2 is irrational is presented. As you see, the user specifies the theorem statement and high-level steps of the proof, and the interactive improver fills in the details between those steps to make sure that the proof is correct down to the level of the logical axioms, which in our case, the axioms of the higher order logic. A main advantage of using interactive improvers is that they can help bypass theoretical hurdles regarding formally proving statements automatically, like for example undecidability or incompleteness, even in the case of mathematics in general. They're also helpful when it comes to debugging a design or a system or a specification or a theorem, because you can always look at where the proof breaks and try to understand why, and then understand where your bug is. Because of these advantages, they have been successfully applied to the biggest formal proof and verification projects ever done, like for example formally verifying a kernel or a compiler or a model checker. So that's why we're trying them in our application here. Although there is no time to give you a satisfactory introduction, I will try to give you an idea of how we technically formally prove that a heuristic is descending. The idea here is to give you a hint as to how to approach such problems using interactive theorem provers. So in our case, there are three main steps to showing a heuristic is descending. The first one is to specify the PDL domain and the domain assumptions and the domain invariants and the heuristic. And then after you do the specification, you parse the specification into Isabelle Hall terms or theory files representing the specification in a language that Isabelle Hall understands and allows you to formally reason about them. And then lastly, you interactively prove that the specification holds. That is to say, you interactively prove that the heuristic is descending. Now let me take you for a quick review of how we currently implement these steps, and I will use notions from a standard planning domain called myconic, to which we applied our method. For specification, we specify the first part of it is the PDDL domain, and this is just a PDDL file which can only include problems in strips in the strips fragment of PDDL, which I assume this audience is aware. The domain assumptions are the second part of the specification, and they are first order formulae in terms of domain predicates, which should hold for the initial state and the goal of any instance for which the theorem applies. So we are restricting what instances of the domain we're reasoning about. So for example, here this domain assumption tells us that we only consider instances whose such that for any atom in the goal there exists an object P such that that atom says that P has been served, and it is also stated that P is a passenger in the initial state of the given instance. Another part of the specification is the domain invariants, which are properties of states which are always preserved along state transitions in any instance of the domain. For example, if we know that an object P is a passenger, then in a state, then this will hold in the next state after a transition. So then we have an invariant saying for all P passenger P. In our case, so finally we have the heuristic, which in our case is specified as follows. So you have this, as stated earlier, capital H, and then the heuristic is just a set of weight feature pairs. So Fi are the features, and they are just functions that map any state of any instance of the domain to natural numbers, and Wi's are the weights. And the value of the heuristic at a given state at S is this weighted sum here. In our case, we limit the features that constitute the heuristic to cardinalities of sets defined using named concepts. I won't be able to introduce that notion properly, but I will just try and convey the intuition. So here, for example, if I say that I want to define the set of passengers that were served, you can use that. You can define that with this named concept here, so that named concept will just be in the intersection of other two named concepts. The first one is passenger, which is the named concept that denotes the set of all objects that are passengers, and another one for served. So and this sign here is the intersection of the two, or the conjunction of the two. These kinds of heuristics are known as tiered measures of progress, and these are the only ones that we consider in our work. After the specification, the next step in our process is parsing. So you parse that specification and produce a model in Isabelle Hall's language of the domain assumptions, and the invariants, and the heuristic. For example, here we're showing the parse concept passenger served. So in order for you to model that concept, you first need to model two concepts. One of them saying that this is a passenger, and the other one, one of them modeling the set of passengers, and the other one is modeling the set of served objects. And then the concept served passenger is just the intersection of both. And look here, this is the conjunction, for example, when it's formalized in Isabelle Hall. To make this parsing possible, we have formalized the abstract syntax trees modeling the different structures of the specification. And in order for us to formalize that abstract syntax tree, we use Isabelle Hall's algebraic data types to do that. So for example, we say that a concept, it can be one of a few cases. So either it's a universe or an empty concept, or an atomic predicate concept, or an atomic goal predicate concept, or the negation of another concept, or the union or the intersection of other concepts. As you can see, there are a few cases where a concept is defined recursively in terms of other concepts, and this is we can do that within Isabelle Hall's data type, algebraic data type implementation. After defining the syntax, you need to define, in order for you to be able to reason about that, objects or structures that are built of that syntax. You need to define semantics, and the way we do that is by defining functions. So here in this case, we have the concept value function, which defines the semantics of the abstract syntax of concepts that I just showed you in the last slide. So this function tells you, given a concept and the state, what is the set of objects that concept represents in that given state. So if you have a concept that is made of the union of the concepts, for example, then the set of objects it represents is the union of the set of the objects represented by the constituent concepts. In addition to the specification, parsing also produces many auxiliary lemmas about the domain under consideration, along with the proofs, and a lot of them are elementary lemmas, like, for example, the actions are distinct, or that the predicates have distinct names, but they still are useful to make the proofs less cumbersome and more automated. After the parsing, we have the last step, which is interactively proving that the heuristic is descending, and I won't be able to show you that because of the lack of time, because I have to actually show you that in a demo session. But to enable interactive proof to be easier, we have taken some steps, and I will just describe those steps. So the first step is that we formalized the notion of potential heuristics and proved many general background theorems about them, which are of general interest beyond our current project, but there's and within the context of our current project, the most interesting theorem we formalized and proved about potential heuristics is a theorem that characterizes sufficient conditions for a potential heuristic to be descending. And that theorem identifies 5 conditions, which we prove interactively for every domain and heuristic. So, for example, it says that the set of features has to be finite, and the features are distinct, and the concepts used to define the features are pairwise mutually exclusive. The interactive part of the proof is mainly just to show that these 5 conditions hold for the given domain and given heuristic. And in order for us to make that interactive part easier, we have developed an infrastructure. So this infrastructure involves 2 things. The first is proving many Gensen calculus or Gensen style calculus rules that allow usable logical automation methods to reason about, for example, concept languages. So, for instance, we have proved this rule for concepts, for named concepts, namely that you can prove that an object X is in the intersection of 2 concepts if you can prove that X is in the first object, and if you can prove that X is in the second object. And this is equivalent to conjunction introduction from a propositional or predicate logic, for example. The second thing we did is implementing automated proof methods that are targeted towards automating the conditions of our characterization lemma, and those methods can prove the first 3 conditions, which I showed you earlier, completely automatically for the myconic domain. But these methods, I would like to note that they are practice-oriented, like many reasoning methods that are implemented within interactive improvers. They are practice-oriented, as in there's no guarantee that they will find a proof, but there is a guarantee that if they do, then the proof is correct, because the proof is checked by Isabel's kernel. Now, I'd like to briefly talk about what we can still do, or what we need to still do. A lot of those challenges are questions whose answer we do not know yet. What's the highest priority? What exactly should we do? Because they are, rather than technicalities that we know, we just need to implement. So we see 2 main challenges. The first one is how much of the proofs can be automated, and that challenge entails 2 questions: a theoretical one, which is about the decidability or the complexity of different reasoning steps, And the practical one, which is about how we implement a decision procedure if one exists, and if none exists, then how can we at least approximate the pen and paper reasoning strategies and implement that. The second question is is related to the interaction between the human user and the system, and this is a question that is considered for many programming language verification environments where the developers or the researchers come up with different interactive modes that are suitable for different programming paradigms, and I think we need to do something like that for planning. And lastly, we want to consider generating domain-specific ASR planners that are have formal running time guarantees based on proving that a certain heuristic is descending. So we want to get an implementation of the heuristic after proving that it's descending. So that's all. I hope you have enjoyed this talk, and I look forward to your questions. Thank you.